All right, so we're going to be talking about trigonometric functions in the unit circle. So first off, what is the unit circle? So the unit circle is simply a circle whose radius is 1. We're going to be defining our trig functions in terms of the unit circle in the future. So coordinates on the unit circle, the radius of the unit circle and such. But simply put, it's just a circle that has a radius of 1 and the center is at the origin. That's all it really is. We're just going to use it to define our 6 trig functions eventually. Some quick basic trigonometry review. So we're talking about stuff you learned in your geometry class. So hopefully you remember the mnemonic device for which sides of the right triangle go with which trig function. So we have SOHCAHTOA. Remember, SO stands for that the sine of an angle is equal to the opposite over hypotenuse. Cosine of an angle is equal to the adjacent over hypotenuse, and then tangent of an angle is equal to the opposite over adjacent. So I have a quick diagram here of our angle drawn in the right triangle. This one here is our angle. The opposite side is the leg that's across from the angle. The adjacent side is the leg that's next to that angle. And then the hypotenuse is the largest side of our right triangle across from the right angle. These are kind of the basics, and we'll kind of use this to help us remember some things and help define them, define our trig functions in a slightly different way on the unit circle and in terms of points and radiuses and such. But this is the basic that we need to remember going into it. So here is a point on the unit circle. So we're going to let P be a point, A comma B on the unit circle. So remembering some things from circular motion that we just talked about, this arc length S, right? Remember our arc length is S, is equal to the radius of the circle times the angle in radians. Well, on the unit circle, the angle in radians is actually the same exact length as the arc, because if our radius is 1 times theta is the arc length. So sometimes you can think about our trig functions as functions that take in an angle measurement, but we could also represent them as something that takes in an arc length as well. Just kind of an interesting way to think about it. That is maybe a little different than angles. We can think about it as an arc on the unit circle. Not super important, but something that we can think about, and it's sort of interesting. And one of the reasons we use the unit circle, frankly. So if we have a point AB on the unit circle, we define our trig functions in this way. Sine of the angle is equal to the B, the y coordinate. The cosine of the angle is equal to A, the x coordinate. Tangent is equal to B over A, the y coordinate divided by the x coordinate. For this to be defined, the A value cannot be equal to 0 because we divide by 0. Now we have these other trig functions. So you probably aren't familiar with these yet. We have cosecant, secant, and cotangent. They're going to be based on the same ideas and same concept as our 3 original. Cosecant is 1 over b, so 1 over the y coordinate, which is the reciprocal of this, right? B is the same thing as b over 1, so it's a reciprocal of sine. Secant is 1 over a, so 1 over the x coordinate, which is the reciprocal of cosine. We take that one and flip it. And cotangent is equal to a over b, so the x coordinate over the y coordinate, which is the reciprocal of tangent. So these functions are very similar to these. They're based on them, related to them as reciprocals. So it's important to note that we are talking about the unit circle here. We're on the unit circle. We're not always going to be given points on the unit circle to discover our trig values. So these definitions are a bit simplistic, and we may need to expand it a little bit when we get off the unit circle. But I want to quickly talk about kind of how they come about. So first, I'm going to just show how we get sine to be equal to the y coordinate. So for any point that's created by the terminal side passing through the unit circle, we can drop down a line perpendicular to the x-axis, down to the x-axis, or if it's in a different location, it could be up to the x-axis, whatever. That's going to allow us to create this nice right triangle. I say nice because, well, the coordinates actually tell us the side lengths, right? This coordinate here actually matches the x-coordinate. Sorry, this length here actually matches the x-coordinate, the a value. And this length here actually matches the y-coordinate, the b value. And since we're on the unit circle, we know this radius has to be 1. So we actually know all 3 sides of this right triangle in terms of the x-coordinate, the y-coordinate, and the radius. And we can use our basic trig relationships, our SOHCAHTOA, to show how these trig relationships actually come about. So that's what I'm going to do here really quick. So SOHCAHTOA, I'm going to show how sine is equal to b. So we have our angle. In this right triangle, however, this angle is going to be the reference angle, the one that we're going to use to kind of discover things about this particular point and its trig values. So this interior angle, this angle that's inside of our right triangle, is going to be the one that we use as our reference. Well, that means that B is the opposite. 1 is the hypotenuse. And A here is the adjacent side. It's the one that's next to the leg that's next to it. Well, sine, based on SOHCAHTOA, is opposite over hypotenuse, which is b over 1, which equals b. That's how we get this. We could do a similar thing to demonstrate how we get all the rest of these as well, but suffice to say it's the same idea, right? Cosine is adjacent over hypotenuse, a over 1a, and so forth. This works on the unit circle. If we're not on the unit circle, we're going to have to expand things a little bit because our radius won't be 1. So we'll have to kind of pay attention to whether we're on the unit circle or not. And we're going to come up with a little bit of a more universal method than necessarily just these, but that's for the future. All right, so let's go ahead and look at this. This is a point on the unit circle. We're not told this, but we could actually figure this out. So these are our xy coordinates. So just kind of estimate where this is. So -1/2 is, somewhere over here, sorry. -1/2 is just, in the negative direction somewhere. And then √3/2 is like 0.87-ish, pretty close to 1. So we'll just estimate that this point is around here. Negative x coordinate, so the left, positive y coordinate, so we went up. So this is a point that the terminal side of some angle passes through. So we'll kind of go ahead and sketch that angle as well. So it passes through this point, which is -1/2 there. And the angle that we're really talking about is right here, or well, this is one of the angles that this could represent. For our purposes, we're going to be dropping down a perpendicular down to the x-axis again. We always go back to the x-axis, either down to it, up to it, whatever, going down to the x-axis to make that right triangle. The leg here is equal to the x-coordinate. That's our x-coordinate, -1/2. And this leg up here is equal to the y-coordinate, √3/2. And since we're on the unit circle, this is 1, but we could show that this is on the unit circle by doing a little bit of Pythagorean theorem. We can figure out what our radius is equal to. So I'm going to quickly show that real quick. So a squared plus b squared equals the radius squared, c squared. Quick Pythagorean theorem here. -1/2 squared is actually 1/4. Plus √3/2 squared is 3/4 equals r squared. 1/4 plus 3/4 is 1. And then the square root of 1 is in fact 1. So we did demonstrate that this point is in fact on the unit circle there, and so that this radius would actually be 1. Sometimes you'll be told if you're on the unit circle, sometimes you won't be. In general, it's good practice and sometimes necessary to discover the radius that we're working with, especially when we're not on the unit circle. All right, so now let's go ahead and figure out the trig values that are associated with these things. This being our A, this being our B. We can use the relationships that are listed right here to figure out the 6 trig values. This is going to be somewhat complicated because we're dealing with fractions and radicals, and there's gonna involve dividing fractions and rationalizing things and such. So it won't be super easy to get some of these, and we'll just look at those as they come up. All right, so sine of the angle is equal to the b, the y coordinate. So sine of our angle is equal to √3/2. Easy. Cosine, again, pretty easy. Cosine of our angle equals the a, the x coordinate, which is just -1/2. Tangent, this is where it starts to get a little more complicated, right? Tangent is equal to b/a, so the y coordinate divided by the x coordinate. So that's two fractions that we're dividing. So √3/2 divided by -1/2. When I divide by a fraction, remember that's the same thing as multiplying by its reciprocal. So √3/2 times the reciprocal of this, which is -2/1. The 2's cancel. We end up with just -√3. -√3/1, but remember, over 1 doesn't actually do anything here. So again, that's kind of a taste of what we're doing. We're going to have to do some operations with fractions, some operations with radicals here as we go through this. So that's our first three, kind of the easy ones here. I'm going to go ahead and do the next three here, but I just need to create some more room. So I'm going to delete these. All right, so next one would be cosecant. So cosecant is 1/b, 1 over the y coordinate. So cosecant of theta equals 1 over the y coordinate. So √3/2. Okay, so here we're really starting to run into it, right? Again, dividing by a fraction, same thing as multiplying by its reciprocal. So I'm doing 1 times 2/√3. That's 2/√3. But we don't love radicals in the denominator, so we need to rationalize this. So we need to multiply the top and the bottom by this radical here to get rid of it in the denominator. So we end up with 2 square root 3 in the numerator, and then √3 times √3 is just 3 in the denominator. So we get this lovely value right here, 2√3/3. Again, you kind of get a taste of it. There's dividing by fractions sometimes, there's rationalizing. This is kind of the complicated processes that come in. The next one won't be so bad, secant. Secant is 1/a, so 1 over the x coordinate. So 1 over -1/2. Again, remember that's multiplying by reciprocal, so 1 times the reciprocal of this. So -2/1, which is -2. So 1 times -2 is simply -2. That one was actually pretty easy. No rationalizing to be done there. And then the last one, cotangent. Cotangent is a/b, so the x over the y. So cotangent of our angle equals a/b. So that's -1/2 over the square root of 3/2. Again, multiply by the reciprocal of the denominator. So that's -1/2 times 2/√3. That's going to equal -1/√3. Right, our 2's cancel. Got to rationalize that. I'm going to go ahead and do it over here. Got to multiply by √3 on the top and the bottom so that we end up with -√3/3. Lovely answer. Not the greatest. I'm being a bit sarcastic here. These processes can be somewhat complicated when we involve the dividing by fractions and rationalizing all the mixture there, but it's simply a matter of evaluating these, taking the coordinates, taking the radius, and evaluating what these trig functions, what these trig ratios would be equal to. All right. Now, our points, the points where our terminal side goes through, won't always be given as a point on the unit circle, but luckily for us, that actually doesn't matter. If it's a point not on the unit circle, well, that just means the radius is going to be something different. But because of similar triangles, I'm not going to get into the details of it, but because of similar triangles, the ratios would be equivalent to if we were given a point on the unit circle. It's very powerful, but means we need to adjust things a little bit. So one of the adjustments we make is right here, an example. So sine of an angle is equal to the y coordinate over r. So instead of just the y coordinate over 1, or just the y coordinate, we're doing the y coordinate over r, because our radius is now r, some unknown number that we'll have to figure out instead of just 1. We're going to look at the rest of the trig functions and how those make adjustments. It's not too complicated, but These are the ones we're really going to want to kind of memorize because they're universally applicable. They will apply even if the point that we're given is not on the unit circle, which is a little more powerful. We can apply them to ones on the unit circle too, and they work just fine, but they'll work for any point. And this is where it's a little more useful than just knowing those strictly unit circle ratios that we were given. All right, so here are the 6 trig functions defined in terms of an xy coordinate that the terminal side passes through, and the radius created by that point, distance from the point to the center here. Again, our radiuses are not always going to be equal 1. Most of the time they will not be, and we'll have to figure them out. So we'll have to do a little Pythagorean theorem. X squared plus y squared equals r squared, right? A, B, C being the hypotenuse. So we'll figure out the radius so that we can then use it in these ratios. And these will be on the future slides so we can kind of reference them. All right, so the point 3, -4 corresponds with some angle theta, and we're going to find the value of the trig function. So let me just quickly estimate where this point goes. So 3 is 2, 3, -4, 1, 2, 3, 4, and we're talking about a point right down here. So that's where the terminal side passes through that point. Our initial side is always on the positive x-axis. And this could be sort of any angle that ends there. So it could be a positive angle that rotates around here. It could be a negative angle this way. It could be multiple rotations. Doesn't really matter as long as the terminal side is there and it's coterminal with this angle. Well, we're going to create a right triangle. So right here, right triangle. And we have some side lengths. We know that this side is 3. Side going down is actually -4 because we went down. In terms of a length of the triangle, we don't care that it's negative, but it does matter for our trig ratios. And we don't know the radius, so we do need to quickly find the radius here. 3 squared plus 4 squared equals r squared. That's 9 plus 16 equals r squared. 25 equals r squared. Oh, okay, the radius is 5. So this is a common Pythagorean triple. 3, 4, 5. It's something we could have noticed and kind of saved ourselves the necessity of doing the Pythagorean theorem. But I wanted to demonstrate that because it won't always be a triple. In fact, a lot of times we'll end up with some sort of radical that we have to reduce or an irreducible one. All right, now we know the x coordinate, the y coordinate, and we just figured out the radius was 5. All of our 6 trig ratios are defined in terms of the x coordinate, the y coordinate, and the radius. So we're just going to simply write these out. Not too difficult. I'm going to do red. I'll do black. I think black shows up well. So sine is y over r. So the sine of this angle that terminates here is equal to the y coordinate, -4 over r. The cosine of this angle is equal to the x coordinate over r, which is 3 over 5. Tangent of this angle is equal to y over x, so -4 over 3. And then these other ones are reciprocals of these. Instead of y over r, it's r over y, and so forth. If it's reciprocal, so cosecant is equal to -5 over 4, r over y. Secant of this angle is equal to 5 over 3, r over x, and then cotangent, which is reciprocal of tangent, is -3 over 4. Technically, the 4 is a negative value, but we don't put a negative with just the denominator. It means the fraction itself is negative. So those are 6 trig values. Those were much easier than the other ones because we didn't involve any fractions and we didn't involve any radicals. So there wasn't any fraction division or rationalization or anything. It was just about writing the ratios based on the definitions that are given to us. Pretty easy in that sense. All right, last example here. Again, we don't think this point is probably on the unit circle. Well, definitely not, because this is -4. That's much more. It's going to be more than a radius of 1, because we have to go down 4. All right, so let's go ahead and estimate where this would be. So it's -2 √5. We could get a calculator out. It's probably a little more than 4. So 1, 2, 3, 4. In the negative direction, we'll just say it's around here for my sake, and then down 4, 1, 2, 3, 4. So we'll put it right there. That's the point we're dealing with. We like to draw it on there just to kind of get an idea of where we're working with and to sketch our right triangle. So that's the terminal side of our angle. Again, the angle could be anything. It could be a positive angle, it could be a negative angle, it could involve multiple rotations, but it just needs to terminate here. Then we draw a right triangle, obviously. We know this side is the x-coordinate, so that's -2√5. This side here is the y-coordinate, which is -4. And we don't know the radius. So we do need to use Pythagorean theorem. This doesn't look like a known triple to me, so go ahead and do that. -2√5. I guess I don't need to think about it as a negative if I'm just using Pythagorean theorem. Because sides aren't usually given as negatives. We use the negative because that's where it's placed on the graph and such. So anyway, 2√5 squared is going to be 4 times 5. That's going to be 20 plus 16 equals r squared. That's 36. And square root of 36 is 6. So radius is going to be 6. That's actually nice that it's a whole number there. It's going to be somewhat convenient. Less radicals to be dealing with. All right. Now, again, there is radical here, so there may involve some rationalizing as we go through, but for the most part, this should go pretty straightforward. There also might be some simplifying here, because actually all of these numbers have a common factor of 2, so some of my ratios I'll probably be able to simplify. All right. Sine of the angle equals y over r. That's -4/6, which is -2/3. Cosine of the angle equals x over r, which is -2√5/6. Again, simplifying here, 1 and 3. So we're going to get -√5/3. That's for cosine. Tangent is y over x. Okay, so that's -4 over -2√5. So a negative over a negative, 2, 1. So that's going to be positive 2 over √5. Got to rationalize. You don't want to leave a radical in the denominator. So we get 2√5/5. Not too bad. As you sort of get faster with this, you can probably make some of these go a little quicker. Cosecant is the reciprocal sign, so it's going to be -3/2. Secant is the reciprocal of cosine, which is 3/√5. Negative, rationalizing, that's going to be 3√5/5. Negative, right, negative. And then cotangent. Cotangent is reciprocal of tangent. I could reciprocal these at any point. This one actually looks like a nice place to reciprocal it. So cotangent of the angle equals √5/2. Positive. Boom. Again, I took some shortcuts there to make this go. You could write them out in terms of their strict definitions and simplify the whole way. We should end up with the same values though. All right. That's the end of part 1. Go ahead and stop right there and see you guys again for the next.